Okay, so let's take a look at the practice questions you had. First set, we're on page 670, number 38 to 41. So 38. Find the electric potential difference stored between charges of 2.6 microcoulombs and negative 3.2 microcoulombs placed 1.6 meters apart. So you're just looking for the electric potential energy, which is EQ, and it's equal to KQQ over R. So 9 times 10 to the 9th Newton meter squared per coulomb squared. One of the Q's is 2.6 microcoulombs, so 2.6 to the negative 6, and the other is negative 3.2 times 10 to the negative 6, and they are 1.6 meters apart. And when you do this, you should get an EQ to be equal to negative 0.0468 joules. And the negative means the field does the work to get them that close, meaning they want to be that close together. And actually, if you field does work, if you were to release them, they would move closer together. They wouldn't move further apart. Okay, you would have to do work to move them apart. Number 39. Two identical charges, so Q1 is equal to Q2, of 2 microcoulombs are placed 10 centimeters apart in a vacuum. If they are released, what will be the final kinetic energy of each? So their R is 10 centimeters, or 0.1 of a meter. So we can find the electric potential energy between them if they're placed this far apart in a vacuum. So 9 times 10 to the 9th Newton meter squared per coulomb squared. 2 to the negative 6 coulombs, and that's going to be squared because there's 2 of them, and then 10 centimeters apart, so 0.1 of a meter. And when you do this, you get an EQ of 0.36 joules. 0.36 joules. But this isn't what the question's asking. This tells us the electric potential energy between the two charges. And they're not going to be happy, right? I'm holding them here 10 centimeters apart, but as soon as I release them, because they're the same nature, one's going to go this way and one's going to go this way. Our conservation of energy would tell us that then whatever the electric potential energy is when I'm holding them here 10 centimeters apart, it all gets changed into kinetic energy when they move apart. Since they are identical charges, they should each get half. And so you would say, therefore, EK is equal to 0.18 joules each. So they would split the electric potential energy between them, and they would both go off with half. Now, if one was fixed, and the other one I brought in and I was holding there and I released it, it would get all of it. But because both of them can move, they will split it. If one was bigger than the other, then it wouldn't be half and half. But because they're identical, it will be half and half. And so you don't have to do any more math than just dividing the 0.36 joules by 2. All right, number 40. How far apart must two charges of 4.2 to the negative 4 coulombs and negative 2.7 to the negative 4 coulombs be placed in order to have an electric potential energy with a magnitude of 2 joules? So they're giving us the EQ this time and both Q's, and they're asking for R. So rearrange for R, KQQ over EQ. So 9 times 10 to the 9th Newton meters squared per coulomb squared. One Q was 4.2 to the negative 4. And the other was negative 2.7 to the negative 4 coulombs for both of them. And it tells us the EQ is 2 joules. Okay, and when you do this, you get an R of 510.3 meters. Now those charges are a bit bigger than we usually use, right? We're usually using micro, and these are only to the negative 4. Because this is a half a kilometer, right? Like, that's still a lot of energy between these two charges. A coulomb is a huge, huge unit of charge, right? And so that's why this would be still a half a kilometer even when it's times 10 to the negative 4. Number 41, two charges of equal magnitude separated by a distance of 82.2 centimeters have an electric potential energy of 2.64 times 10 to the 2 joules. What must be the sign and the size of the charges? So this time you're looking for the q's, and they say they're identical, so we could write it as q squared and then rearrange it for q squared. So q squared will equal r eq over k. And so they told us they were separated by a distance of 82.2 centimeters or 0.822 meters. EQ, they told us, was 2.64 times 10 to the 2, or 264 joules. And K, of course, is 9 times 10 to the 9th Newton meters squared per coulomb squared. Now, when you do this, this will be Q squared. You'll get 2.4112 times 10 to the negative 8 coulombs squared. Take the square root. Of course, you know when you take the square root of anything, it's plus or minus 1.5528 times 10 to the 4th coulombs. So this is the size. Now the plus and minus, just to make sure we're clear, what that means is either both are negative or both positive. So either both positive or both negative. So it doesn't mean one is positive and one is negative, because if that was true, they'd be attracting each other, and these ones aren't. Okay, so that's that page. And that's it for the electric potential energy. But then I asked you to flip over to page 678, and I asked you to do... sorry, lost what I asked you to do. I asked you to do number 43. So I skipped 42 just because it was not actually a potential difference question. So 43, how far from a positive point source of 8.2 coulombs, so my Q is 8.2 microcoulombs, I think. Was it micro? No, it wasn't. It was just coulombs. Ooh, that's a huge charge. Will the electric potential difference be 8 volts? And then in brackets, it says 8.2 coulombs is a huge charge. I should have mentioned that to you. Okay, so it tells us it's the source, and it's asking how far, and it's giving us a V and a Q. So you're going to use V equals KQ over R, and you're going to solve for R. So KQ over V. Okay, so 9 times 10 to the 9th Newton meters squared per coulomb squared. Q is 8.2 coulombs, and the voltage is 8 volts. And when you do this, you get an R of 1.476 times 10 to the 10th meters. Like, that is a huge distance. Think back to when we were doing planets. Like, that's bigger than, like, or the Earth from the Sun is times 10 to the negative, times 10 to the 11th. So this is comparative to the charge being on the Earth, and you're finding the potential difference almost at the Sun. So it gives you a feel for how really huge a coulomb of charge is. All right, I skipped 44, and I asked you to do 45, which says... the electric potential difference at a distance of 15 millimeters, so R is 15 millimeters, from a point charge is negative, so V is negative 2.8 volts. What is the magnitude and sign of the charge? So again, V equals KQ over R. So this time Q is going to equal V times R over K. 15 millimeters is 0.015 meters. V is negative 2.8 volts. And K is